For this last but certainly not least talk of the year, we have the pleasure of having Marletta from Cardiff, who will speak about the Laplace operator with boundary conditions singular at a point. The stage is yours, Marco.
Thank you very much. I'd like to thank you, Alexandre, and thank Jean as well for organizing this series of seminars. I've been to many fewer than I would have liked to attend, thanks to having other things to do, unfortunately, like, pesky things like teaching students. It's clearly been the most successful of a large number of successful analysis seminars across the world, and it is a privilege to be invited to speak in it. I'm going to be following a kind of pseudo tradition that exists in various ambits, not just in seminars, but in other aspects of life too, that when you do the last one before Christmas, it's maybe not as heavy, not as scientifically as serious as some of the others. So I'm going to talk about a problem which I see that Uzi Smilansky is here, so he's going to hear the story of this from my point of view for the first time. So he knows the story from his point of view, and now he's going to find out how it seemed to me at the time. So let me get this thing going. No, it's not happy. Okay, good. So, this is a problem. It's a problem that was posed by Michael Berry and Mark Dennis. Mark Dennis was still in Bristol at that time. And the basic idea of this problem is that you've got some domain in R2, nice domain, it can have a C infinity boundary, I don't really care. And inside this domain, you want to satisfy your favorite differential equation, minus Laplacian u equals lambda u. And then on the boundary, you've got a boundary condition. And the boundary condition that Berry and Dennis considered was this one. So they've got u plus some function. S here is, I don't know, maybe arc length, signed arc length along the boundary, I don't know. U plus f du by dn equals 0 on the boundary. And at some point on the boundary, this function f has got a simple 0. So I'm thinking here of an f that's bounded, it's piecewise continuous, differentiable away from any discontinuities and so on. So at some point on the boundary, this f has got a nice simple 0 at some point where it's continuous and differentiable. And this was the problem that they were considering. So when you're a physicist and you write the problem like this, it honestly looks quite harmless, right? So they had gone and done some calculations, and they believed that the spectrum of this problem was real, and that every point of the real line was an eigenvalue with an L2 eigenfunction. And Uzi told us about their paper. So they published a paper about this in JPhys A. And I guess they were quite puzzled by some of the features of this problem. So when I say Uzi told us about their paper, or Uzi told me about their paper, what I mean is that Uzi was actually in Cardiff at the time, and he invited me to come round to his office so he could tell me about this problem. And he was doing some calculations using semi-classical methods. And try as I might, I've never really managed to develop a good intuition for semi-classical methods. So I sat there for about 40 minutes trying to pretend as best I could that I actually understood these very elaborate calculations that Uzi was doing. And eventually I managed to escape, and I went back to my office and I decided, well, goodness, I'm not sure I'm going to manage to do this, understand this problem at all. So anyway, in fact, the story is that the problem is not symmetric. So far from being self-adjoint, it's not even symmetric. As it stands, any operator that you might naturally associate with these two equations is going to be the adjoint of a symmetric operator. So you're going to need, its domain is going to be too big for a self-adjoint operator, too big even for a symmetric operator. And so you're going to have to equip it with some extra boundary conditions. And if you can work out what those boundary conditions are, then it will turn out that this problem has not just eigenvalues going to plus infinity in the usual way, but it's got eigenvalues going to minus infinity as well. So it'll be you'll get a self-adjoint operator with compact resol-vent, whose eigenvalues, however, go to minus infinity. Now, usually, when you want to prove some sort of thing about, the eigenvalues of Laplacian going to plus infinity, you use some compact embedding results. You use the fact that, say, H10 is compactly embedded in L2 on a nice smooth bounded domain. But here, the eigenfunctions are not going to be in H10. Many of them are not going to be in H1 at all. So there's going to be a different method for showing that this problem has got compact resol-vent. The positive eigenvalues will satisfy a Weyl law, but the negative eigenvalues are going to be very different in the way that they're distributed. So the negative eigenvalues go to infinity very rapidly indeed, exponentially fast in the index, in fact. This epsilon here is the derivative of f at the point where it vanishes. So that's what the eigenvalues are going to look like when the index goes to minus infinity. Okay, so the story of how Gregory and I came to be involved together on this is that I think we both went away having been told on separate occasions about this problem by Uzi. We did pretty much, I imagine, the same calculations, and then Uzi put us in touch with each other, and we wrote a paper about it, which also went into JPhys for the enlightenment of the physicists, if I can say that without sounding too patronizing. I worry sometimes these days that I might say something that's perfectly acceptable today and might get me into serious trouble tomorrow. Anything that goes on social media.
Get you into trouble right now.
I'm in trouble right now, okay.
Because I know that paper a little bit, and they just double checked, and nowhere do they claim that every real number is an eigenvalue, and they write down, they do numerics for the eigenvalues. They do write that there are negative eigenvalues which are going to infinity and negative infinity. So it's not that they didn't know what was going on.
Well, they wrote several papers on this, okay.
I only know one, the JPhys one.
Yeah. So maybe it was Uzi who claimed that all the real numbers are eigenvalues, but certainly there was a claim that
I think Uzi is capable of defending himself.
Okay, so let's get on and look at how you have to deal with this paper. With this problem. So if you look at the problem with gosh, just about any kind of general method for PDEs, you don't get very far with it. I know that Gerd Grub had tried to look at it. And actually, I think she wasn't entirely happy that we had been involved in this as well. But here's what I did. I went back to my office, and I looked at the problem in the geometry that where you can actually do all the calculations explicitly, and that geometry is a semicircle. So if you look at the problem on a half disk, this D-shaped region, let's say with Dirichlet boundary conditions around the perimeter here, and on the straight edge here, you put this boundary condition. So your f here, f of y is epsilon times y and vanishes here. So f is linear with a nice simple 0 there. And the nice thing about this setting is that mirabile dictu, when you separate variables in polar coordinates, this boundary condition here becomes this boundary condition here. So u plus epsilon du by d theta is 0. So now this is a constant coefficient boundary condition, which I guess somehow makes it even more unlikely at first sight that it's going to cause you any trouble. I mean, if you were just to flip this around and write it as du by d theta is -1 over epsilon u, then it doesn't look bad at all. Okay, so it's really surprising in a way that this is going to cause us such an interesting spectral structure. So you associate an operator to this in the usual way, so that your maximal operator here is going to be the set of all u in L2, whose Laplacian, interpreted in whatever weak sense you like, is also in L2, maybe interpret it in a distributional sense, for example, and satisfies this equation. That's the domain, and then the action of the operator is just LU equals minus lambda u. And now you go away and you actually do the calculations that you would ask a second year undergraduate to do. So you, let me move the Zoom controls out of the way because I can't see what on earth I'm doing here. Okay, so you do a separation of variables in the usual way, and the angular part here satisfies this differential equation, and you can write down the eigenvalues explicitly. So there's a lowest eigenvalue mu0, which is -1 over epsilon squared. And then all the other eigenvalues are just the squares of the positive integers, which, by the way, is what you would get if instead of that funny boundary condition on the straight edge, you had just the Dirichlet condition. Okay, so one extra eigenvalue here compared to what you would get with a Dirichlet boundary condition. The eigenfunctions, of course, are somewhat different, and I've written them down here. Correct up to normalizations, which I was too lazy to calculate. And then your Laplacian decomposes like this. So minus Laplacian of u is given by this expression. And so the Laplacian admits this orthogonal decomposition. And here the nth operator ln is given by this expression. So mu n, remember, here is -1 over epsilon squared for n is 0, and it's n squared for all the others. Now, what about the domain of un? So the domain of un is basically the set of all u for which that expression there lies in a weighted L2 space. And then, of course, you've got to stick in your one remaining boundary condition that hasn't been captured by these conditions on the angular eigenfunctions up here. So you've got to impose your Dirichlet condition on the outer circular boundary there. This weighted L2 space here, I'll just remind you what that is, or tell you what the notation is. If I can get Zoom to change the slide. Yeah, there it is. So there we go, there's our weighted L2 space. And that's very natural that you would expect to have that weight there because of the usual formula for change of the element of area in R2 from Cartesian to polar coordinates. And here's the basic fact that makes the problem interesting. All the ln, when n is greater than or equal to 1, are self-adjoint. but L0 is not. Okay, so you don't need any extra boundary conditions on Ln for n greater than or equal to 1, but you are going to need to do something about L0. So let's see what's going on with L0. So for this purpose, I need to invoke some kind of fairly old technology. So let's try to understand what the behavior of the solutions of this differential equation. So you'll see I've thrown away the lambda dependent part here, arguing that, well, when r is small, then that's going to be negligible compared to, say, this guy here. So let's do an ansatz. In fact, doing an ansatz for this equation, a power ansatz, actually gives you the exact solutions of the equation. So when, I should say when n is not 0, sorry. When n is not 0, then the solutions of the differential equation are r to the plus and minus n. And only the one with a plus sign is in the weighted L2 space. So you always have a moment of anxiety about the n equals 1 case, depending on what powers you might have up here. But even the one with r to the minus 1 is clearly not going to satisfy this condition here. So for each n greater than or equal to 1, this differential equation has, up to scalar multiplication, only one solution in L2 with weight r. For n is 0, on the other hand, the solutions look like this expression here. Okay. So you can see that they're infinitely oscillatory near 0, but you can also see that they're bounded. Okay, so they're what are you going to do? I mean, the situation, roughly speaking, is that this is as if you had a normal regular differential equation of order 2. You would expect to need 2 boundary conditions for it, and you've only got 1. In these other cases, you've eliminated one equation, one extra solution by imposing this weighted square integrability condition here. But here, imposing that condition doesn't do anything in the case when n is 0. So you're going to need an extra boundary condition. So the deal here is that L0 is of what's called a limit circle type, and it needs an extra boundary condition in order to become self-adjoint. Okay, so the standard Titchmarsh-Weyl theory with 1990s Anton Zettel enhancement describes what this boundary condition has to look like. So the boundary condition, you take these two solutions here, U0 and V0, which give a basis of the solution space for the case lambda equals 0 for the operator L0. And then a general boundary condition has this form here. So it's just like a general Sturm-Liouville boundary condition. So you've got a couple of parameters, A and B. So A and B only need to have this property here. You know, I could call them cos alpha and sine alpha, for example. And then you've got these funny square bracket things. And these funny square bracket things are the limiting value as r goes to 0 of this weighted Wronskian. So once you know what U0 and V0 are, you don't get to choose those guys. But once you've chosen your A and your B, okay, once you've chosen your A and your B, then any function U on the domain of a self-adjoint realization or a self-adjoint restriction, sorry, of L0 has to satisfy this condition here, in which F is U and G is basically AU0 plus BV0. So that's the deal. So that if you make that restriction and define the operator L0 dash to be the restriction of L0 to the kernel of this linear operator here, then you get a self-adjoint operator. And this is all classical stuff that's been known since, well, a long time, certainly. I mean, in different parts discovered at different times. The fact that you can get away with considering only the solutions for lambda equals 0, that was probably the last significant contribution to this theory of 1D boundary conditions, and that's from the early 1990s. Now, of course, at this point, you'll say, well, Marco, but we started with a PDE here, and you're describing your boundary conditions in terms of ODEs. Can you describe the boundary conditions in terms of the original PDE? And you can. You can go away and do a little bit of a calculation, which I've written down here, but which honestly I feel almost not really motivated to explain. But the outcome is the following: that the so-called boundary condition for your PDE is this rank 1 condition, which is that the elements of the domain of your self-adjoint operator, U, have to be such that their Laplacian is orthogonal to U naught theta naught. Okay, so sorry, that's if you're choosing the boundary condition with A is 1 and B is 0. So if you're choosing the boundary condition with A is 1 and B is 0, then the condition is that Laplacian of U has to be orthogonal to U naught theta naught. Theta naught is that lowest, is the ground state angular eigenfunction. And then more generally, I think there's something written under here, but I can't see it because the zoom controls are in the way. But I imagine that what you're looking at there is a condition that Laplacian of U is orthogonal to AU naught plus BV naught theta naught. No doubt somebody will complain if that's rubbish. Okay, so that's it's very unusual, I think, with PDs to need a boundary condition that's just a rank 1 boundary condition. And also, it's not, in some sense, a boundary condition. It's a global condition. It's a non-local condition. Orthogonality is a non-local condition. Whereas in the ODE setting, it looked like a local condition. Okay. Now, what can we say, having done all that? Let me try and get zoom controls out of the way because I cannot see the top of my own slide here. Right, so this is a slide about eigenvalue asymptotics. So let's now first look at the eigenvalues for the, so here's our self-adjoint operator, our self-adjoint partial differential operator. That's our limit circle oscillatory guy, now equipped with the extra boundary condition needed to make it self-adjoint. And then here's the direct sum of all the other guys, which are already self-adjoint. So this is self-adjoint. Now let's see what we can say about the eigenvalues. So for these LNs, the expression for Ln is this thing here with an n squared. And as I said before, this is exactly what you would have if you put in Dirichlet boundary conditions. And so the direct sum starting with n is 1 is unitarily equivalent to the Dirichlet operator. And so in particular, therefore, the eigenvalue asymptotics for this part of the direct sum are what you'd expect for the Dirichlet Laplacian. So they're the usual Weyl asymptotics. Now, of course, we also have this chap here to worry about. And we know he's got negative eigenvalues, but let's say we have decided that we're not going to look at those negative eigenvalues yet, and we're going to look only at the positive eigenvalues and ask, are they going to mess up our count? Because, I mean, there's going to be infinitely many of them. From general abstract nonsense, you can prove that they tend to plus infinity. And so there's going to be infinitely many of these guys. Will there be enough of them to mess up the Weyl asymptotics that you would expect from this part for the positive eigenvalues? Well, there aren't. because it turns out that the positive eigenvalues for this guy satisfy a one-dimensional Weyl law. So they are much more sparsely distributed than the eigenvalues for the rest. So at least to leading order, the presence of this operator here is not messing up your Weyl asymptotics for the positive eigenvalues. Now, the negative eigenvalues have this different and much more sparse count that's written here at the bottom of the slide. I wish there were a kind of, I wish there were a beautiful proof of this. I mean, in the paper where we wrote it, at some point we decided we kind of couldn't be bothered keeping track of all the constants and so on anymore. But at least to leading order, that this is what the count looks like for the negative eigenvalues. So they're much, much more sparsely distributed, and they're going to minus infinity exponentially fast. Now, I'd like to say something maybe now about the constants in this process. So how fast do these go to minus infinity? And does the speed at which they go to minus infinity in any way depend on the rest of the domain in the problem? Because at least from this expression here, all you're seeing is the epsilon that came from the derivative of the function at the origin. So you're not seeing the rest of the domain here in that epsilon. You're not seeing even your extra choice of boundary condition. And in fact, that's correct. So to leading order, you don't see the rest of the domain, and you don't see the boundary condition. And that remains true if you change the rest of the domain, okay? So the rest of what I'm going to mention is going to be some work that was done by my former PhD student, Freddie Simons, who is now a researcher at the Fondazione Bruno Kessler in Italy. So he did this work as one small part of his PhD. And he proved that if you basically make the domain bigger, then the leading order asymptotics won't change. And I'd like to explain the method by which he did this, because it's one of my favorite methods. It's Glassman decomposition, and it's combined with a second one of my favorite methods, which is block operator matrices, and then that's combined with a third one of my favorite methods, which is sure complements. So we'll stick together three of my favorite cheap tricks for dealing with problems and see that we can get a bit more information about the eigenvalues. So let's suppose this is our domain. It's not meant to be in any way symmetric anymore. Just this was convenient. It's more convenient to draw it to look that way in ticks. So what I'm going to do is I'm going to assume that there's an arbitrarily small segment of the boundary here that is straight. And on that arbitrarily small segment of the boundary, we have that Berry-Dennis, that strange Berry-Dennis boundary condition. And then over the rest of the boundary, I honestly don't really care what's going on over the rest of the boundary, except it has to be nice. I don't want any more Berry-Dennis chicanery going on anywhere else on the boundary. So the way that we deal with this is that we cut the problem along an artificial boundary that we introduce here. You can introduce these for doing numerical calculations as well. So this is a semicircular artificial boundary, and you introduce the Dirichlet to Neumann maps from the inside and from the outside. Okay, and what I've done here is I've represented these Dirichlet to Neumann maps as infinite matrices with respect to the basis of the angular eigenfunctions that we saw earlier on across here. So in that basis, because this inner part is nice and symmetric, and the operator has that nice diagonal decomposition, diagonal fibration, the inner part of the Dirichlet-Neumann map admits this 2x2 block operator matrix decomposition, in which this thing here, this m of lambda, is a scalar function. It's a Neven-Linna function, as it happens. It's the Titchmarsh-Weyl m function associated with the operator L0. And this thing here is an infinite diagonal matrix. And this infinite diagonal matrix on its diagonal has the Titchmarsh-Weyl functions for the operators Ln. So this is an infinite diagonal matrix whose diagonal entries are all Neven-Linna functions. And I've just picked off the first one and left the rest all there wrapped up in that big matrix there. Now, what about from the outside? So from the outside, everything is much more as you would expect it to be. So again, I'm going to represent it with respect to that same basis, but your outer Dirichlet-Neumann map, because there's no crazy stuff going on out here, then this is not going to have the, well, it's going to be something of this form, and we're going to have to work out what we can say about these functions a, b, and c. So a is going to be again a Herglotz function, an Neven-Linna function, just a complex valued function. B will be a complex valued infinite vector function, and c is going to be the rest of the Dirichlet-Neumann map, which will behave pretty much the way that you would expect it to if you were dealing with a nice regular Dirichlet problem. So we're interested here in the negative eigenvalues. So negative lambda less than 0 is an eigenvalue if and only if the kernel of the sum of the Dirichlet-Neumann maps is non-trivial. So you have to be able to find some vector in the kernel of the sum of the Dirichlet-Neumann maps. And it's stronger than that. You can prove that the first entry in this vector can't be 0. Why can't it be 0? Well, you see, if it were 0, then it would turn out that what you had is you would have managed to prove that this thing here, m of lambda plus c of lambda, had a non-trivial kernel, and that's not possible when lambda is negative, because these two operators are both strictly positive when lambda is negative. So the kernel entry, the kernel element of this operator has to have this form. Okay, of course you don't know what h is, and h will in general depend on lambda, but then we're going to find lambda as part of this process. Okay, so now you do a sure trick, you do a sure decomposition trick. You solve the equation for h, and you find that this equation here is now the differential equation for the eigenvalues. And the, sorry, differential equation, it's the equation for the eigenvalues. So this is just saying that the eigenvalues are the zeros of this now complex valued analytic function. Of course, you do have to worry, I suppose. I mean, this is an infinite vector here. Notice that is transpose and not transpose conjugate. Everything here is analytic in lambda. But basically, the deal is that when lambda is negative, A, B are all nicely well defined. M plus C is analytic and invertible. And so all the bad stuff is here. So this M of lambda here, I told you that's the Titchmarsh-Weyl function for the L0 operator. I'll draw you a picture on my board of what that looks like. Let's see if I can stop the share. Actually, I'll write that formula up in the board before I switch over to the board. Okay, so I will share something else now. I will share second camera. Get a bit more light. Maybe too much light. I don't know. Can you read this?
Yes.
Is anybody there?
Yeah, I can. Yeah, I can.
Okay.
Yes,
I had a moment of paranoia there. My internet crashed earlier this week, and I gave 30 minutes of a lecture before I noticed that there was nobody there. So right, the eigenvalues of the zeros of this thing. Now, all of that is being a good boy when lambda's negative. Nothing crazy is going on with that. This thing here, on the other hand, this is the Titchmarsh-Weyl function for your operator L0. So if you were to draw a graph of that as a function of real lambda, then it would have poles going to -infinity very rapidly, obviously. And the way that it behaves at the poles, it is like that. Okay, so it always blows up in that way. So if you want to know, where does this thing have zeros, you almost don't really need to know what the rest of this function is doing here. You just draw a line through the thing, and you can see that you're going to get zeros. Well, it's not very apparent here, but if you imagine that these are getting really far apart, really exponentially large, and in particular, that this is blowing up like crazy, then you can see that the zeros of this thing are going to be really close to the poles of M. So you go and you dig down in Freddie's paper to see what you can find. I'll go back to the slides now. Okay, so you go back, you dig into the formula in Freddie's paper, and what you find is that the negative eigenvalues satisfy an asymptotics like this. So the epsilon is what I said it was before. I said, I remember these words coming out of my mouth now. I said that this constant here doesn't depend on the extra boundary condition chosen. That's actually not true. This constant here does depend on the extra boundary condition chosen. So that's where you see the extra boundary condition. That's where you see the epsilon from the boundary condition that we started with. And here's the remainder term. And this remainder term is of order mod lambda to the -1/2. Okay, so this next term down, when you've multiplied it out, is of order square root lambda. So you may be able to see, well, you will be able to see some information about the rest of the domain in these terms here, but we haven't actually done a sufficiently neat and detailed and precise analysis of what's going on with these functions A, B, and C in order to know precisely what information about the rest of the domain is in these remainders here. So you've got this huge amount of very rapidly growing negative spectrum that seems to carry really very, very little information about the whole of the rest of the domain that's attached to it. Okay. And I think that that's essentially where I want to wrap it up today. I know that probably the organisers wouldn't go nuts if a normal, decent speaker spoke for another 5 or 10 minutes, but being neither normal nor decent and cognizant of the fact that Christmas is almost upon us, I think I'll stop here, and then you can ask as many questions as you like. Thank you very much.
Thanks a lot, Marco, for this presentation. Do we have any questions for Marco?
May I, Michael?
Yes, Michael, you may.
Yeah, I have two questions. First one, you stated that all the theorems are the case when the zero on the flat part of the boundary.
Yes.
Is it technical or is it really essential that the boundary is flat?
It's not essential. It's honestly, it's essentially our laziness. I mean, I'm absolutely certain that you could do a local change of coordinates to make the boundary locally flat, and it would not perturb these results. That I'm absolutely sure about. I'm just honestly too lazy to go into that level of technical details for a problem where I'm not entirely sure how interested people are in it. It's a crazy little problem. Okay. I should say, by the way, that there's one part of this story, so it's already been pointed out, I got myself into trouble with Berry and Dennis. There's one last thing I should say in order not to get myself into trouble with Pavel Exner, who for all I know might be hiding there among the participants. Yes, he is.
I'm here.
Okay. So the kind of last part of this story is that I think apart from the eigenvalue asymptotics, essentially, this was all done long before Berry, Dennis, or any of us came along in a paper of Exner and Sheba in 1988. Okay, so
we didn't care about eigenvalues.
They should get the original attribution.
Yeah, we didn't care about eigenvalues. We had a half plane with these crazy boundary conditions.
Mm-hmm.
Right, but you would still get eigenvalues, I think, even with a half plane. Yeah.
Sure.
Yeah.
All right. I see a hand raised from Grisha Barkalaiko, so if you want, you can.
Thank you. Would the situation change drastically if you expand this point, the 0 point, you just, like push the linear parts away and stick an interval of Dirichlet conditions in between the linear Raban type conditions?
Yes, it would change drastically, because as soon as you put a little Dirichlet interval in between you've got this function f that has a symbol 0 at one point, right? Gosh, no, sorry, I'd better be careful. No, I'd better be careful. I was going to say the spectrum would then be could then be bounded below, but no, I think the spectrum would still be unbounded below, because the unboundedness from below comes from what's happening on one side of the singularity. So adding a Dirichlet bit on one side in between the two bits would not change it, because you would still have the problem that you would have, if you go and write the variational form of the problem and write down formally what comes off the boundary, the integral term off the boundary, you would still have the bit that at least formally looks unbounded below. That wouldn't go away. So the answer is no, it wouldn't change.
But what if you cut off the, the linear, sorry, just exactly the function that you have there, just on an interval around 0, you just plug in 0. So the Raban condition on the left and on the right never go
Oh,
to
I see what you mean. So you never let you mean you never let f even approach 0.
Yeah.
So in that case, your spectrum, of course, will be then bounded below.
And then you can take the limit and see more and more negative eigenvalues emerge, sort of thing?
I'm guessing so, yes. I'd be pretty surprised if that didn't happen. I mean, you can, because the problem separates so nicely in this geometry, you could do these calculations almost explicitly.
Okay.
But yes, that would happen.
Okay, thank you. Thank you very much.
Thanks for this question. Do we have any other questions for Marco?
And if you have like 2 bad points, will things be really different, or can one say something?
No, the thing here is each D point, as Michael Berry called them, somehow is its own little universe. It doesn't really see the rest of the world.
Okay, okay.
Yeah, so I mean that's kind of the key to understanding what Pavel said a moment ago, that even if you look at this problem on a half plane, you still get eigenvalues going to minus infinity. So the more each D point will generate its own little set of eigenvalues going to minus infinity in some way.
Okay.
Something like a point interaction, so everything is local.
Mm-hmm. Okay, thank you.
All right, thanks, Dima. Do we have any other questions? All right, well, it was great to finish this semester of talks with the Marco's talk, which generated a lot of discussion. So thanks again, Marco, for this very nice talk.